Last but not least, Gergely new.
Thanks for sticking around. So the clicker, maybe. All right. Thanks a lot. Okay, so I want to thank you for staying. So this is joint work with my friend Lorenzo, and it's about iterate averaging as regularization for stochastic gradient descent. So another talk about stochastic gradient descent. Final one for today. Okay. So more narrowly, this paper is in the context of linear least squares regression. This is a very well-known setting. All of you know. Well, you have some covariates X and some labels Y. You have some D-dimensional covariates, where D should be thought of as like very, very big or even infinite. Okay, and there's some distribution generating this data. All right, and then your goal is to minimize the squared risk, right? So you're looking for the best linear predictor, W star, that is going to minimize the squared loss based on NIID observations. Okay, so it is well known that the optimal solution for the population version of this problem is given by this W star, which is just the inverse covariance matrix applied on the vector EXY. Okay, so we're just going to assume without loss of generality that this inverse exists. And otherwise, we're going to assume nothing about the smallest eigenvalue, okay, just that it's positive. And we are going to make some minor technical assumptions. So we are not assuming that the model is well specified. We assume some bounded kurtosis, some bounded label noise. Well, okay, so if you want to discuss this, just come to the poster, right? So it is well known that the reigning champion for this problem is stochastic gradient descent with a fixed step size and iterate averaging. So stochastic gradient descent in this particular problem takes the following form, that you just update your iterates in the following direction. And then you take a uniform average of these iterates, and this is called Polyak Ruppert averaging. Okay, so this is just looking at all the iterates that you have computed and taking a uniform average over them. So this was proposed by Boris Polyak and David Ruppert simultaneously. And it was shown very recently by Bach and Moulin in 2013, and there was a lot of subsequent improvements made to this, in particular by Gergely, Flammarion, and Bach, who proved the following result. Essentially that the excess risk of the average computed this way satisfies the following bound, so that it is composed of a so-called variance and a bias term, where the variance term is the sigma squared d over n, where sigma squared is the label noise, so to say. And the bias term is essentially the norm of the optimal solution W, and it goes to 0 at a rate of 1 over n squared. So what's remarkable about this is that it matches the rate of empirical risk minimization, which is the statistically optimal solution for this problem, up to some higher order terms that vanish more quickly. And this is essentially the price that you pay for using an iterative algorithm. Okay, so this is standard, but this is kind of useless if D is very, very large, or in particular infinity. So if D is very, very large, then, well, the folk wisdom says that what you should do is actually regularize, right? So not run stochastic gradient descent on the squared loss objective, but add some L2 regularization squared, L2 norm regularization on top of this objective, run stochastic gradient descent, and turns out, from the work of Gergely, Flammarion, and Bach, that if you do this and take a uniform average of the iterates again, then what you get is a bound of this form where, well, essentially this first term is still the variance term, and it involves a certain effective dimension kind of term, right? So this is this trace right here. So this is essentially independent of the dimension if your covariance matrix satisfies certain assumptions. For details, we can talk at the poster, all right? And then essentially this norm that the W star is measured in, it also depends on lambda and the covariance. All right, so basically the bound takes the following form. You have sigma squared d over n, where this d is now the effective dimension, and you have this W star norm, and this goes to 0 at a rate of 1 over n squared, but there is a remaining bias thanks to the regularization, which is proportional to lambda squared in this case. Okay, so this is all very well known. So what I'm going to tell you now is a different fancy version of iterate averaging that gets you the same guarantee in a kind of surprising way, or, well, you're going to decide if you're going to get surprised or no. All right, so this is what we do. We do stochastic gradient descent with a fixed step size eta. Okay, so this is what you've seen. But now, instead of taking a uniform average of the iterates, what we do is we do a geometric average of the iterates. But this is not the geometric average that you've seen before in this session. This is actually an exponential average of the iterates. So the way to read this is that this gamma is going to be a parameter between 0 and 1 over lambda. Okay, so this weight is going to be between 0 and 1, which means that I put a large weight on my initial iterates, and then I'm going to decay this exponentially as I progress. Okay, so the later iterates are going to receive less and less weight somehow. And this is just there for normalization. Okay, so this is what we do, and what we claim is that this geometric averaging scheme has the very same effect as doing SGD on the regularized objective and then taking a uniform average. So in particular, this is the main theorem that we show. So if lambda is a positive parameter and gamma is chosen in this particular way, so it is basically a scaled version of the learning rate eta, so it's eta plus something small, okay? Then we have the following bound. I'll let you inspect this for a few seconds. So this looks very much like what I've been showing before. In particular, the second bias term, it looks exactly the same. So this is the exact same term, right? So the norm of W star in this lambda norm that is scaled by the same 1 over n squared plus lambda squared kind of thingy. And here you have the sigma squared d over n plus something else. Okay, so this is just some extra variance. So what you can observe that, well, this is the same thing, and gamma is this effective step size. If you replace gamma with eta, then you're gonna get the same exact thing, up to this additional variance term, which we can explain. Well, come to the poster, and I'm gonna tell you about it, okay? But the main story is that the usual safe choice for regularization, which is just setting lambda as 1 over gamma n, it continues to work fine. So this extra variance is not going to ruin the party for us. Okay, so then you can ask me, okay, so why is this true? Like, what is going on here? So the intuition is that this geometric averaging, it induces a kind of shrinkage, right? So since you're weighting the initial iterates higher than the later ones, it somehow pulls you back towards the origin or wherever you started from, right? So you're trying to regularize in this way your iterations. But actually we have not just this intuition, but a very, very profound connection between this regularization scheme and Tikhonov regularization. So what we show in particular is that if you let this procedure run for long enough and take this geometric average, then this is actually converging to the ridge regression solution. So this is converging to the exact same solution as if you would have run stochastic gradient descent on the regularized objective and took the average. So this is somehow the heart of this result, which was the original observation that motivated this whole procedure. So this is, I think, quite surprising. And if you knew about this before, then please tell me about it, because somehow it feels a little obvious. This is all the proof. I'm not going to walk you through this right now. Again, come to the poster, please. Right. So, but if you don't believe the proof, or if you don't have enough time to verify it, I can show you a figure. Okay, so so just run SGD, which is going to be the blue line, and then if you take different averages of this, so in particular, if you take a uniform average, that's going to be like this reddish line. So that converges to the OLS solution. And if you take this geometric average, then it actually converges to the ridge regression solution, which is that circle over there. So if the math is not correct, then this has to be correct. Well, right. Okay. So then you can ask me, okay, why is this good? I mean, it's cute and everything, but how can I use this in practice? So we could come up with one application. I mean, we of course really like the result, but there is an application as well. So it gives you a way of finding your regularization parameter by post-processing, right? You just run stochastic gradient descent once, right, with a fixed step size on your data. You store your iterates, and then you just pick your regularization parameter lambda, and then you just realize different averagings with this, right? You just compute different averages, and then this has a huge advantage over running SGD from scratch for every different lambda. Because observe that this averaging operation is non-serial, right? So you can parallelize it to an arbitrary extent. So this can be like super, super fast on a GPU, if you like. So you can tune your regularization parameter like super fast. So this is what we could come up with. But basically, we just did it because it was beautiful. Yeah. So if you contrast this geometric averaging with another very popular averaging scheme, which is tail averaging, which is, well, putting more weight essentially on the final iterates that you would compute. So it turns out that these methods have complementary uses. So these are the formal propositions, but this is the takeaway message from them, that if you have small or poorly conditioned data, right? So if your inverse covariance matrix has a huge rank as compared to the number of data points that you have, then geometric averaging has an edge because it actually reduces the variance. And otherwise, if you have large data or if you have well-conditioned data, so for example, if the smallest eigenvalue of sigma is large enough or n is large enough, then tail averaging has an edge, as was shown by Pratik Jain and collaborators recently. Okay, so this and both of these methods can be realized by post-processing the iterates, right? So you just run them once, and then you just play around with these lambdas or the tail averaging parameters, which is pretty nice. And well, okay, if you look deeper into the analysis or this proof that I was showing to you, then you can actually observe a close connection to early stopping as well, because the proof, or at least this short proof that I was showing, goes through introducing a geometric stopping time. And it essentially shows that if I run batch gradient descent for a random number of iterations, then this has the exact same effect as second order regularization again. But yeah, for the other details and discussions, please come see me at the poster. Thanks.
Thank you. Maybe one quick question to